Okay, hi everyone. My name is Huseyin, and thank you all for coming to this session. About me, I have worked for several companies for their microservice and DevOps transition, and currently working for Hazelcast. And in this session, I will just try to provide some production-grade experiences aggregated from these previous projects. Beside that, I am trying to do regular talks to the community and doing some workshops time to time. So let's start. A quick outline here, because I just wanted to mention about a couple of priorities. I mean, since we will talk about in-memory data on the cloud environment, we just wanted to focus on the business logic, and I will try to mention about why this infrastructure abstraction part is important. And beside that, there is some specific terms. Maybe you have just heard about this, the control and data plane. Since we are trying to provide a service to the customers, this we will talk a bit about the resource management also. Most of the in-memory technologies just supports the persistent part, and I will mention how to do that in cloud environment. Of course, since you will have lots of customers, then the monitoring is the key part. Finally, I will show how to provide an access to customer for your actual service. So let's start with the first part, the infrastructure abstraction. When you try to create a SaaS service, right? There are different kind of cloud providers. So each of them has different terms, different resources. And if you just wanted to do a pure implementation on all cloud providers, you will see there will be lots of exceptions. So you need to have a good expertise on each cloud providers. So is there actually any other way to do this? So how can we eliminate those kind of class-specific terms and just focus on the business logic? On my case, I am trying to use Kubernetes for this kind of environments. For example, Kubernetes, maybe you haven't heard about this. This is just an open source container orchestration system for managing application deployment and scaling, and this kind of related applications. So you have an in-memory technology, and you can just easily deploy, do some kind of scaling operation, resource management operation in an easy way, in a cloud agnostic way. But you need to think about this. Kubernetes does not create your infra part. So you need to, you are the responsible one for the entire infrastructure. But Kubernetes lets you to form a cluster by using that VMs. So there is an actual architecture for this. Kubernetes at least needs this one. But don't worry about this, because almost all the cloud providers has this Kubernetes as a service, and you can just go and click a couple of buttons, and that's all. So you have the Kubernetes cluster. And also there are lots of integrations on this. You can use Terraform in order to create your cluster in different kind of cloud providers. Okay, we are talking about abstractions, but is there any example on this? Let's say that in Kubernetes environment, if you create a service with type load balancer, actually it will create a load balancer in the cloud provider. So you don't need to know how you can create a load balancer on Azure, on AWS, or on GCP, whatever other cloud providers. And also, we said that persistence, and here you will need some kind of volume, disk. This term's always changing. And in Kubernetes world, you can just create a PVC, and then it will create a disk, volume, etc. for you on the background. You don't need to know this. And also, we talk about application deployment. In order to do this, there is a tool which is called Helm. You can just handle the unified application dependency management. If you have an in-memory technology, you can just create an Helm package, provide some reasonable configuration, and that's all. So when you jump into this world, I mean, shipping this kind of projects to the cloud environment, most probably you will think about this, the control plane and the data plane. So you can just have a look at this picture, and there are two parts, right? The first part, which is your actual services workload exists, and the right-hand side is the place that your actual technology the one that you provided to the customer exists. When we say control plane, it is the place where you orchestrate your SaaS system, right? For example, you are providing some kind of technology to the customer. You have a control plane on this. The first capability of this plane is just do a business validation before creating an actual resource on Kubernetes. So what is this actually? You have a service, SaaS service, and you have customers, right? They just wanted to subscribe your system. There can be different kind of subscriptions. Based on their plane, you create different kind of resource, different kind of clusters. When a customer tries to create a cluster, you need to do a business validation, and this is handled inside the control plane. And this control plane is capable to connect any kind of destination. What does this mean? If you have a service, it can be something like regional, multi-region service, right? I just go to the console, your application, and then provided my cluster name and selected cloud provider and the region. So based on your selection, your control plane, you can call a set of microservices. And from this microservice pool, there is a service which is called cluster service. It is capable of connecting to any kind of Kubernetes cluster on the data plane. And these cluster credentials and the details can be fetched from a secure source, let's say that database. And this control plane also can listen a couple of events and decide on the next step based on the metric collection, right? For example, if your cluster memory is more than 80%, maybe it can trigger a scale-up operation. Or if you do not allow to do a scale-up operation, maybe you can notify the customer. So there can be different kind of options. Those three are the basic operations that can be handled inside the control plane. So what is the data plane on our case? Here you can see this box is only for the technology you provide the customer. And you can see again, there can be different kind of node pools, right? Based on your requirements. These pictures and the components actually form the data plane. Inside the data plane, you may have your actual technology, and also you may have different kind of agents for this. For example, this is these agents is for the management and the monitoring purposes mostly. And this data plane may have a private or public network topology. So we will deep dive into this in the following sections. And also this node pools term is important because a customer selects a cluster type on your screen, and based on the selection, again, you may select different kind of machine types on the background, right? And they all have different reasons. For example, CPU intensive, memory intensive. Okay, you just selected these machine types and you use them for the actual technology. Let's say that some kind of MySQL, for example. And here you have used that one, but you just wanted to dedicate this machine VM for the actual technology. But what about the agents one? So for the agents, you may not need this kind of strong machines, right? For example, if you you are in the AWS environment, you can select something like T2 medium, maybe it is enough for you. So that's why we just create a node pools. You can say node pools, node groups. It also have different kind of naming. So what about the application deployment part? If you have an in-memory technology, you can just create an health package. Most probably it will need a Docker image. So you need to dockerize your technology first. And this Docker image will be an input to your Helm chart. And in this Helm chart, whatever configuration you have in the normal world, they can be converted into an options inside the Helm chart. So when you search for any kind of popular Helm chart in the GitHub, you can see lots of examples there. But time to time, if your deployment strategy is very complex, for example, it is not a simple deployment, but you need to create lots of side components. Maybe you need to track something inside your deployment. This time, you can use the operator instead of a normal Helm chart. This is just an advanced topic, but you can just search for Kubernetes operator in order to create some kind of custom resources for you. In the first option, you can just do stateful set deployment to create and deploy your technology. But on the second part, beside this deployment stateful set, you can just introduce these new custom resources to the Kubernetes environment. So you have a system, and this system is being used by the different kind of customers, right? But since you are providing this to multiple customers, there is some challenges. When you create a cluster on EKS, AKS, or GKE, you will see that actually they spin up a VM on the background. For example, on GKE, when you create a cluster, just go to the compute engine and see whatever they all created a VM on the background. Okay, this is just simple. But let's say that you are about to create a cluster. I mean the in-memory cluster. Here, customer selected in total 16 gigabyte of cluster. You cannot just use 2 M5 large on the background. So M5 large has 8 gigabyte of RAM and 2 CPUs. So here you can, theoretically, 2 times 8, which is equal to 16 gigabyte. That's it, but it may be wrong. Let me provide a concrete example on this. AWS, Azure, GCP, we have 3 type of machines here. And AWS, Azure is nearly same. They are nearly same. But when you have a look at the GCP part, CPU is same, but the RAM part is 7.5, right? Okay, when you create a Kubernetes cluster on AWS, you will see that this total RAM, out of this total RAM, the 100 megabyte will be used for hard eviction threshold inside the Kubernetes system. So they are providing a service, but they need to reserve some part of it for their internal purposes, right? 700 megabyte will be used for operating system plus the kubelet. So kubelet is one of the important components for Kubernetes clusters. And we say that we will use Kubernetes in order to deploy our in-memory technology very easily. So we need this one. And in total, you will have 7 gigabyte usable memory for the pods. So when you say M5 large, it is not 8 gigabyte. Actually, it is 7 gigabyte. So you need to think this kind of operations. Just have a look at the Azure part. When you create a cluster, and let's say that you are using this machine type, and you will see the first hard eviction, it is very, very bigger than the first one. And they reserve 1.8 gigabyte of memory for operating system and kubelet, and you will see you will have 5.4 for the usable memory port. Yeah, so this is very important. You see the difference. And on GCP part, the hard eviction is same with the AWS. The operating and kubelet with very, very same, nearly same with the Azure. And you will see the 5.6 will be usable for the memory and pods. And first of all, you need to know your infra limits. So you need to have these values in some place. Of course, there is some calculations for the CPU part, and you can just have a look at this part in the Kubernetes documentations. So let's say that I know my infra limits. I just selected a machine type, and I know how much memory available in this system. Let's switch to the pod resource management. If you are providing a service to the customer, multiple customer, and then this pod resource management also is important. They should be properly defined. And also, this pod resource management is handled by requests and the limits. So let's have a look at these terms one by one. When you say request, actually you are saying that how much memory CPU needed for this application, right? When you say limit, actually up to how much memory CPU can be used by this application. Let me provide a physical example on this. I have a pod, which is named metric consumer. When you provide those details, in order to schedule this pod to the Kubernetes environment, you need to have 300 megabyte of memory, at least 250 millicore CPU, at least in your system. if you do not have this available memory and CPU, your workload will not be scheduled into the Kubernetes environment. Okay, let's say that you succeeded on this. This time there is a limit value. So limiting is an important part because maybe based on the customer selection, you need to put an upper limit in order to not to affect the other customers' clusters. Here, when you say 600 megabyte of memory at most, your cluster is overloaded, and then your cluster may need more memory, right? But it can be up to 600 megabyte on this case. And also with the CPU part, it can be 500 millicore at most. So those values are just about the design. So while you are designing your system, you need to think about this part. Okay, until this part, we talk about the Kubernetes, the infrastructure abstraction. And now we are talking about, but what about the persistence? We say in memory, but at the same time, we are saying persistence. In most of the in-memory technology, there is somehow a persistence support, right? Here, persistent means on demand or with a configuration. Whenever you write the data into the memory, time to time, it can be synchronized into the disk. So this is very good for the disaster recovery scenarios. And it may be challenging, but in a distributed system, it is challenging than other stuff. In this diagram, let's say that I have a Kubernetes cluster. I just deploy in-memory technology inside this Kubernetes cluster. In the green box, you can see there are the nodes, physical nodes of the Kubernetes cluster, and they all form a Kubernetes cluster. And when you deploy an in-memory technology here, actually every cluster member, in our case, we have 3 cluster members. They are actually pods, right? For example, when you use stateful set or deployment, they will just schedule a pod. And if you need a persistent support on this part, you can maybe use the first option, the managed file storage service. What is this? If you are using AWS, there is a component which is called EFS, Elastic File System. When you try to create these pods, you can just use PVC in order to schedule a volume for you, right? This is not a simple EBS, but it just reserves a volume for you inside the central file storage service, and you will contact with this service over the network. When you say I need 5 gigabyte of data, this PVC will reserve something for you, and your data, you see there is different folders for each node, for physical nodes, in this central file storage service. So this is the first option. But you need to think about this is, you need to do some kind of maintenance for this, and not all of the major cloud providers support this one. It may be a bit tricky. Let me provide you the second way. In the second way, again, we have a Kubernetes cluster, and in-memory technology inside it. This time, when you use persistent support, let's say that I just trigger a snapshot operation. When you do that, the data will be stored inside the pod. And since I have used PVC, this pod has a volume mount with the physical node, underlying node, in this case, N1, N2, and 3. Okay, when you do a snapshot, it will be written in the pod, and it will be synchronized to the physical nodes. But what about the storing part? I mean, the central part. You need to involve another member here, candidate here. Let's say that there is an uploader agent. This uploader agent checks for the file changes, and if there is a new data, it automatically uploads this data into an object storage. Let's say that you are using GCP, you can use object storage, and if you are using AWS, you can just use a simple S3 bucket. Here, what I am doing is I am trying to upload this data to an S3 bucket. Most probably this bucket is specific to customer. And you see there is another folder which is cluster. It can be a cluster ID. And within this cluster folder, you will see 3 different folders, N1, N2, N3. This can be a node name, or it can be the cluster member name. I don't know, it can be 1, 2, 3. But when you go to this directory hierarchy, you will see the actual backup data. You need to involve another candidate here. But this scenario can be challenging, but since we are providing this kind of features in memory specs, we need to handle this one in the cloud, right? But what is the real motivation on the background of the persistence? You can just take a snapshot at a time t, right, for your cluster. But why we are trying to do a snapshot operation? Because in the future, we can just restore from the snapshot for the disaster recovery. It is not just for on the customer. Let's say that you are just taking the daily snapshots or hourly snapshot, whatever it is. If there is a problem in your SaaS service system on the underlying architecture, infrastructure, you can just collect all the clusters, just use the recent snapshot and just resume or restore all the clusters. You can do the disaster recovery. Or there is another scenario, which is the customer can manually take a snapshot from the UI, and then they can just clone another cluster by using this instance snapshot. This is a very cool feature. Let's say that you have a prod cluster for your prod environment. You can just want it to reproduce something or test something. You can just click the create snapshot and then create another cluster out of this snapshot. Let's say that dev cluster. So you see the data is replicated to the dev part. Of course, there are lots of alternatives. Maybe you can do one replication or other stuff, but this is just for the in terms of the persistent support. Here, you see, I just talk about an agent, another candidate. So here, let's say that there is an uploader agent. So if you have 3 nodes, for example, you need to have 3 uploader for in total, right? Because since the data is inside the node of the Kubernetes cluster, there should be some agent right beside this node to access this actual backup data. And in order to distribute this uploader agent, they are same, because in order to distribute them to Kubernetes nodes, you can just use the daemon set. And most probably there is a downloader agent also. But why we are using downloader? It is another daemon set. So the main motivation of this downloader is, let's say that you are about to restore a cluster, right? When you try to create a dev cluster out of the snapshot, inside your orchestration, you just need to trigger this downloader agent first to download data first, and then just create your cluster by providing this downloaded data as an input to your cluster. So that's it. Within your configuration, provide the path. The data is there inside the physical nodes. That's it. So here we are talking about downloader, uploader, and they are contacting to object storage. It can be S3, it can be storage admin, or in Azure, you can use some storage containers, right? But how these agents are able to access this system? So maybe you are providing a physical credentials, but it may not be some secure way, because it can be seen by the customer somehow. But there is another term, workload identity. As an example, in GCP, when you search for this workload identity on GKA, you will see something like this. The cloud provider creates a service account for you. You just created a service account. And maybe you know, inside the Kubernetes, there is also a service account. This workload identity lets you to map this service account in the cloud provider with the service account inside the Kubernetes environment. And you can just provide some kind of roles to your service account. When you do that, in our case, if I am using the GCP, I am using Golang client of the GCP. And when I say new storage.upload, for example, this Golang client already knows how to resolve credentials. It can first check, for example, environment variable. It can check static credentials file, or it can try to connect to metadata API inside the Kubernetes system and then resolve the credentials and let you to upload anything or download something from the object storage. So this is introduced to GCP in this year, I think, and there is equivalent technologies in other cloud providers. Okay, you have multiple customers. They are using it. let's say that every customer has at least 2 members in their clusters, and you have 100 customers. When you multiply it, you will see there are 200 components inside your system. But there's a question here. How are you monitoring this part? Since you are using Kubernetes, you are not only abstracting the infrastructure, also you introduce lots of simplicity into your system in terms of this kind of installation, monitoring, etc. In Kubernetes world, there is an open source project which is called Prometheus. By the way, you can use Prometheus in on-prem environments. This is not specific to Kubernetes environment. Here, when you search for the Prometheus, you will see a basic architecture for the monitoring part. Here, we have different kind of components. The first one is the Prometheus server. It is the actual core, the brain of the Prometheus. So it has an API. By using this API, you can do different kind of operations. For example, there is another component which is node exporter. This node exporter actually knows how to collect metrics from the Kubernetes world. It can collect metrics, for example, disk values, CPU status, and also it can connect some kind of C-advisor endpoints. But you can also provide your custom exporters and just put these exporter URLs inside the configuration. It's so flexible. There is a push gateway component, the other one. So by using this component, you can just send your metrics to the Prometheus and another alternative. Let's say that you have a central Prometheus system, and the system, the network that you are collecting your metric is inside a private VPC, let's say that, and the Prometheus cannot access your system. So in this case, you can just push your metrics from your private VPC to this central Prometheus system by using push gateway. There is another component, alert manager. So you are collecting lots of things, but if you are not aggregating, not playing with these metrics, it's useless because you just use your disk, right? Nothing else. Since you have metrics, you can just create rules, and then alert manager will do the next action for you if there is some matched rule. So the next step can be notifying someone via email, sending notification, or they can create an on-call notification in this PagerDuty option, this kind of systems. Here, Prometheus says everything for you, but you need to think something. When you jump into Kubernetes world, you shouldn't do some kind of static configuration. So we are talking about Prometheus configuration, but in order to add some kind of alert manager config, you shouldn't just change with the files, right? The config files of Prometheus. Instead of doing that, there is already a built-in feature. When you use Prometheus operator, you will see it will come with the additional resources, custom resources. So remember the Helm section in the package management. You can use just Helm chart, or if you have a complex system, you can just use the operators. Here we have Prometheus operator, the community project. Let's say that you just wanted to define a rule. If any kind of cluster have more than 80% memory usage, just notify the customer, or just maybe scale up the cluster, right? You can just define Prometheus rule, and when you do that, it will be involved in the alert manager rule list automatically. Because when you define some kind of new rule by using these custom resources, there is a Prometheus sidecar for this. It will automatically detect it and reload these configs automatically, and then you will be inside the alert manager rule list. As a destination, this can call an endpoint. Maybe you can also just call a REST endpoint in order to scale up your cluster, right? Or maybe your cluster is not active for last 1 day, then you can just stop or sleep the cluster if it's a free one. You can do that. But let's say that you have 100 clusters and you install Prometheus monitoring system inside it, but is that it? How you manage it actually? So there is a problem in one of the customer. What will you do next? You can just jump into customer cluster and have a look at the Prometheus screens, or is there any other better way? Here, you can just use a central monitoring system. Let's say that you design a setup for this monitoring one. But when it comes to high available and scalable system, you may think to involve tunnels into your monitoring scenarios. So they are very, very same components, but let's say that if you need a scalable and highly available Prometheus version, just use the tunnels. Let me try to show you some diagram for this monitoring. Again, we have 3 members of the clusters. I have in-memory technology, 3 members. Sorry, not 3 members. I have 3 clusters. You see there are 3 Kubernetes clusters. Here, Prometheus is already installed in every Kubernetes clusters. You see there is a Thanos sidecar. This Thanos sidecar already knows how to collect metrics from Prometheus. So it collects metrics from Prometheus and sends it to Thanos receiver. Remember this Prometheus operator, by using some kind of configuration and options, you can just enable Thanos and provide your receiver URLs, etc. When this Thanos sidecar send metrics to the Thanos receiver, and Thanos receiver is responsible for putting this data in the object storage based on the retention period. Let's say that it collects data every time, real-time data. And if some data is 1 hour old, they can automatically store it inside some kind of object storage. In our case, for example, AWS S3. So we have a real-time data in Thanos receiver, and also it is somehow a snapshot in the S3 bucket. If you need some kind of metrics, you need to just contact the Thanos querier. When you do some kind of query on the Thanos querier, it will automatically connect the Thanos receiver. But when it needs some kind of old data, let's say that, it will connect to Thanos storage gateway. And Thanos storage gateway knows how to extract data from the S3. And in order to do some query, for example, there is already a language for this, PromQL. And all the data you see in the Prometheus part, they are stored in the PromDB. So instead of handling this monitoring stuff on every cluster one by one, Kubernetes cluster one by one, what I did is I just injected sidecar, Thanos sidecar, and right now I'm able to collect every metric into one central monitoring system, which is the Thanos query on my side. And the final step is I just involved Grafana into the entire scenario, and Grafana knows Thanos query as a source. When you try to find something, that's it, the metrics in the Thanos query. And also you can create some beautiful Grafana dashboard by using these metrics. We talk about alert rules, but when I try to provide some examples, for example, is if the used memory inside the cluster in memory technology, then you can notify the customers maybe because they haven't enabled the auto-scaling feature in your cluster, then it will be better to notify customer. So this is a very good rule. So customer know that, okay, there is a 80% usage. Okay, I need to go to the console and maybe scale up my cluster manually. Let's say that I just enabled the auto-scaling feature as a customer for my cluster. Then if the memory usage is less than 40, then scale down the cluster. So how this scale down operation will be handled? As I mentioned, since these metrics is already shipped to a central monitoring system, the Thanos querier can be consumed by Grafana, or the Thanos querier can be consumed by one of my microservice, right? So let's say that I have a job for this, something like cluster metric consumer, something like this. So it continues to check the Thanos querier. If there is a used memory less than 40 and the auto-scaling is enabled, it can directly call scale down operation by calling another microservice, and it will connect to data plane and change the stateful set replica set or deployment replica set or re-execute the Helm chart, right? And if the used memory is more than 90, then you can trigger a scale-up operation. So since you have everything inside your monitoring system, you can apply any kind of pipeline in this system. Inside the Prometheus operator, you can just search for the Prometheus rule. They are just like deployment pod definition. They are just another custom resource. Very simple. Okay, in order to deploy our in-memory technology, we used Kubernetes. we just set up the monitoring system, not to be blind in terms of infrastructure monitoring. And now everything is working. It is time to provide an real access to the customer, right? The first thing you need to think is the network topology. Based on the needs, these clusters, I mean in-memory technology clusters, can be inside a private or a public network. While you're creating a Kubernetes cluster, all the cloud providers already provide this network topology type while you are creating some Kubernetes cluster. And here, the real challenge is accessing the public cluster is okay because you just create a Kubernetes cluster, the in-memory technology is inside it, and let customer connect to this cluster. That's simple. But what about the private one? We are putting this cluster inside a private network. It can private VPC. There is no connection from the outside. They all have a private IP set. So what is next? Let's see. Here, if the cluster is public, there can be different strategies based on your technology. For example, if you are using, on our case, Hazelcast, I need to connect these cluster members one by one. I need to know every member. Of course, there is another strategy, way, but in order to have a better performance, I need to use this notation. So if you need every in-memory technology cluster member one by one, you can just expose your technology members to the outside by using NodePort service. This is the first way, you see. In the second way, you can just put a load balancer or expose this service as a load balancer service to the outside. So there will be only one connection point, and the request will be automatically load balanced to the backend services. Okay. But we are talking about NodePort, but you cannot do in Azure. This is just an exception because by design, they are not supporting this NodePort while you are exposing something to outside. But in this case, there is a solution. You can use just meta controller. What is this? You can just create a resource for meta controller, and it will listen your services, NodePorts. If you have 3 members, it will automatically create 3 load balancer for you. So you see, I have 3 entry points to the system, but they are just load balancer, but they are not acting like a load balancer because they actually have only 1 member on the proxy part. So we are talking about this kind of endpoints, but what about the connection part? So in the Kubernetes world, you cannot just talk about the static host names and the IP addresses, right? Of course, you can do that. For example, if you have a Kubernetes cluster, when you deploy something in memory technology, you can just provide some elastic IP addresses to the nodes. But you'll know that it is not a cheap technology. And also, there is a limit for that. Instead of playing with the static host names and the elastic IP addresses, you can just use another way. So since we are dealing with the Kubernetes environment, you can just consume Kubernetes events. So I am a customer, created a cluster in memory technology, deployed it. So inside my agents, let's say that I have a separate agent, Kubernetes consumer. You can just connect to the Kubernetes cluster in cluster connection, just consume the events. If there is something change within your pods, it can directly send this change IP addresses to a central cluster member management system. Here, you can easily get the member private IP addresses, public IP addresses. And when I call my microservices to store them into the database, the next step is very simple. Inside your client part, the connection part, user needs to hit some kind of endpoint, and this endpoint will return a public port pairs to the response. So right now, you can just connect to the cluster because the IP address pairs, port pairs there. Let's say that something changed. You scale down the cluster. Again, since you are listening the Kubernetes events, you will know that, okay, this pod is deleted. Then I need to remove this member from the system. When you do that, you will see in the response, you will have only 2 members. We are talking about service discovery, connecting to them, but what about the private clusters? Even you store private IP address, you cannot just connect them because They are totally closed outside. In order to succeed on this, you can just use peering, right? It has different naming on different cloud providers. For example, in AWS, it is VNet peering. In AWS, it is VPC peering. So this scenario is nearly same on all the peering scenarios. First of all, customer creates a in-memory technology in your console, and then you need to provide a pre-generated CLI command. I assume that your service already have a CLI, and you just provided a CLI, pre-generated CLI command. When customer copies it and then execute it on their workstation machine, it will just initiate a VPC peering on the customer side. So this part is important because I don't know anything about the customer part, because they just get the CLI, execute on their side. But you need to prompt user in order to collect at least two information. For example, AWS peering part. You need to ask for VPC ID and the subnet, because in order to do VPC peering on AWS for different accounts, you need to provide account ID, but I already know account ID because inside the CLI command, I already have an AWS SDK, and I am just calling, for example, get caller identity. I already get this account ID programmatically, nothing problematic. But I need to prompt for VPC ID and subnet, because you're about to decide to allow a connection to your actual private cluster on our side from your actual workload. You have a company account, you already have a set of microservices, and now these microservices, we use it in memory technology as a cache endpoint, right? So you need to select proper VPC ID, proper subnet. You just initiated it. Okay, this is the first part. And the second part, once this CLI successfully initiate the VPC peering connection, it sends a request to your control plane again. Why? Because it just succeeded on the customer side, just send a notification to control plane to finalize the remaining parts. I don't know if you know about AWS VPC peering, but when you just create a VPC peering on the owner part, you need to provide cross values to the peer part and do the same operation in order to make an active connection. So send request to control plane, and control plane already knows that, because most probably you are providing at least the cluster ID, right? So your system knows that, okay, there is a VPC peering initiation, let me try to complete it. When you do that, there will be an active connection between the customer company accounts workload and your actual in-memory technology. So in AWS, we are talking about VPC peering. In Azure, it is called VNet peering, and in GCP, it is called VPC network peering. And when you have a look at the requested parameters, in AWS, you need to provide account ID, VPC ID, and subnet. In Azure, it is VNet ID only needed. In GCP, project ID and network name is okay. So we are talking about VNet VPC peering, but there are some kind of different technologies. For example, in AWS, there is another linking technology which is called private link. And by using this private link, you can just convert your actual service into a marketplace item. They are actually will be converted into a VPC endpoint service. So that is another bonus information on this. Okay, since you initiated VPC peering, right now there will be a direct connection from customer account to the actual in-memory technology. Here, there's some advanced cases, but you need to carefully track this operation also, because, for example, there can be some inter-region communication, right? The customer account inside the US West 2, and they deploy their cluster into some kind of AP South 1, for example. There can be a huge I/O between the customer and the cluster. So you need to carefully track, for example, to I/O operations here, because otherwise there will be some huge additional cost, and somehow you need to include this cost into customer bills. This was another side information. So that's all about this in-memory technology shipping to cloud.
Okay. Well, thanks everybody for attending this session. The next session starts in a little over 10 minutes, and we'll see you there. Thanks, Huseyin. Have a good day, everybody.